Now we are ready to talk about the main result. Before actually telling you the main result, let me just remind you of this parameter D, which was the proxy for the network sparsity in the model. And for kidneys, this D was somewhere between 4 to 15. That's the key parameter by which I'm going to state all of the results of the paper. Now we get to the main theorem. In steady state and for large values of m, the assumptions that I described for you in the previous video, the fraction of agents who die under the greedy algorithm, the fraction of agents who perish under the greedy algorithm, is at least 1 over 2d plus 1. And the fraction of agents who perish under the patient algorithm is at most e2 minus d over 2 divided by 2. So if you combine these two, you get the last line. So that's not super important. The key point is that the loss under the greedy algorithm is 1 over 2d plus 1 at least, and the loss under the patient algorithm is at most e2 minus d over 2 divided by 2. If you set a reasonable value of d for the kidney market in the United States into these two equations, you immediately see that the loss of the patient algorithm, the algorithm that weights and only matches critical agents, is at most 17% of the loss of the greedy algorithm. So this is just telling me that the value of weighting in a world in which weighting cost is 0, that's very important because that's not the world we live at. But in a world in which weighting cost is 0, the value of weighting is huge. The upper bound on the value of weighting is huge, and this motivates us to go and actually study the weighting cost and then analyze the trade-off between weighting and weighting cost. But now this only tells you about the first part of the previous graph that I showed you, the gains from timing. Now, in order to complete the picture, I have to tell you what are the gains from network optimization, and that's the second important theorem that I'm going to show you now, which is that the loss of the optimum algorithm, the algorithm that weights, matches only critical agents, and whenever deciding to match a critical agent, optimizes over the whole network structure. I don't know how that algorithm works, but I can use some random graph techniques to bound the performance of that matching algorithm. And here is the bound that I can find, which is that the fraction of agents who perish under the best possible algorithm is at least e2 minus d over e2 minus d over 2 divided by d plus 1. And recall that the loss of the patient algorithm was upper bounded by e2 minus d over 2 divided by 2. And this is basically telling me that gains from timing are much more important than gains from network optimization in this model that I constructed for you. In fact, if d is 8, which is again a reasonable number for kidney market, then the loss of the greedy algorithm is going to be roughly 8.5%. The loss, or the fraction of agents who perish under the patient algorithm would be 0.9%. And then the loss of the optimum algorithm would be somewhere between 0.9 and 0, and this just tells me that most of the gain is achieved by merely being patient. Now let me show you the last graph, which summarizes all the two theorems that I showed you. On the x-axis I have d, the network sparsity parameter. On the y-axis I have loss, the fraction of agents who perish. The blue graph that you see is the lower bound on the loss of the greedy algorithm. So if you greedily match agents, if you try to match as many agents as possible as soon as they arrive, then your loss cannot be below this blue line. The red line is the upper bound, the red curve is the upper bound on the patient algorithm. So if you are patient and match critical agents, but then be completely local and naive in which agents to match, then your loss cannot be more than this red curve. And the green curve is the lower bound on the best possible thing you can do. And as you can see, this green curve and this red curve are a little bit, distant from each other when d is small, and that's because this red curve is actually making lots of mistakes. But as we move on and increase network sparsity, then actually most of the gain is achieved by merely being patient, and the network problem is solved due to market thickness. In the next video, I'm going to talk to you a little bit about the proof ideas beyond these two theorems, and you will see how beautiful random graph techniques are going to be applied in this matching problem.